Well, I'm excited to head down to Starbase for the fourth flight of the Starship coming up very soon. And I thought that I would do some preliminary analysis on the performance of the booster, specifically after the hot staging and return back to the Gulf of Mexico. Also using some of this new information that we got from SpaceX following Flight 3, and also do a comparison between a return to launch site profile for a Falcon 9 as compared to what we saw with Booster 10 on Flight 3 and also for Booster 11 coming up for Flight 4. So how I'll do this is we'll use the footage from Flight 3, as you can see here just before hot staging, and we'll also be doing comparison video images of Falcon 9s along the similar profile, comparing speeds and times. Now what's going on here is of course the hot staging, and this upper image shows you a similar scene for a Falcon 9, and at the bottom left you can see the engines are all lit. Now with the information that SpaceX provided, we know that all 13 of those engines did start, and for the majority of the boost back were lit, but 6 of them had a premature shutdown, and you can see that during our discussion. This also caused to some degree some variations in the return profile. Now because those 6 engines shut down, when it came time for the landing bird, they were not available, so we were unable to get the full amount of boost or engine ignition and thrust for the landing, and that caused some additional issues which we will discuss further. An important part of this analysis and discussion has to do with the composition of our atmosphere and the conditions that the booster faces on the return flight. Now on the left-hand side of the screen you can see the layering of our atmosphere. It starts with the troposphere at the lowest altitudes, and it works its way all the way up to the thermosphere near the 100-kilometer Kármán line location. And you can see how temperature varies throughout this area. At the lowest troposphere area, there's a standard lapse rate, which is about 3.5 degrees Fahrenheit per 1,000 feet, or about 2 degrees Celsius per 305 meters as we go up in altitude. And on the right-hand side of the screen, we can see how the pressures of the atmosphere change. And what's the most important, and I want to show you between the ground level and 50,000 kilometers, is that at about 5,500 meters, we have 50% of the atmosphere lost. And then at about 17 to 18,000 meters, we lose an additional 90% of the atmosphere. And above that, it rapidly goes to zero. And we'll see that in millibars during the discussion. So here we return back during the boost back of Booster 10 during Flight 3, and you can see the speed is rapidly decreasing. That is because the boost is retrograde, or opposite direction to where it was traveling initially when it let the Starship go during the hot staging. The bottom left, you'll see those 6 engines shut down prematurely, and then the rest of the engines at the end of the boost back, and of course the comparison to the Falcon 9 in the upper right-hand corner photo. Now what I want to show you is how the booster follows the profile that SpaceX uses for the return. And what you'll see is on the right-hand side, the arrow following this kind of a loop that brings you up into altitude and as part of the boost back maneuver. And the bottom left, you can see how the speed is decreasing, the altitude is increasing all the way up to the apogee, or the highest point. If we compare to the Falcon 9, it's about 22 kilometers lower and about 13,000 kilometers per hour slower than a Falcon 9. Here we can see how the speed is now increasing as the booster is falling back to Earth, and also in the right-hand side of the screen you can see how the arrow is following along that loop trajectory that SpaceX uses for both the Falcon 9 and for the booster for Starship. And we'll continue to follow this all the way down through the Kármán line, which is generally the altitude where we say that we've left the atmosphere, or in this case returned back into the atmosphere. And then we'll continue to follow this profile all the way down to 90 kilometers, where we'll take a look at more of the discussion of what is going on with the booster. So here I'll freeze it at 90 kilometers. I'll give you a comparison to a Falcon 9 at 90 kilometers as well, and its speed at the time. And then this is a chart of a Falcon 9 that I put together based on this particular profile. This gives you an idea of where the entry burn occurs and how the speed scrubs off between about 49.9 kilometers to about 30 kilometers in altitude. Also, it's important to note that the Starship booster does not do an entry burn, and you'll see that in the comparison of the profile. Now, also, this can vary from Falcon 9 to Falcon 9. This is just an example. It just depends on the performance of the particular mission that they are in, but generally this gives us a great idea of what to expect and what to compare to. You can also see the atmospheric pressure on the right, how it is changing, and where the 10% of atmosphere and 50% of atmosphere occurs during this return profile. So here we'll continue to follow the Booster 10 on Flight 3 from 90 kilometers down. I'll show you here this inset showing you the decrease in altitude and the layers of the atmosphere that it is transitioning. Also note how the temperature is changing during this time period. Now, to help set up the further discussion that we're going to have later in the video, I wanted to show you the comparison of the return profile for Booster 10 during Flight 3, that's in the blue with the stars, and a Falcon 9 return to landing site profile. One of the things that you notice right off the bat, and I'm showing you here in this oval, is that without the entry burn that Falcon 9 does, at 30 kilometers, Starship has a lot more energy to dissipate. In fact, it's about 1,600 kilometers per hour faster at 30 kilometers in altitude than Falcon 9. And all of this is going to need to be scrubbed off via aerodynamic drag. I also wanted to point out Booster 10's Flight 3 performance issues on the return, starting at about 21 kilometers and following this profile down to where the engine landing burn ignition attempt was made but failed. And this also coincides with where the atmospheric density and pressure starts to rapidly rise, going from very little to about 10% atmospheric pressure and density, all the way up to 50% atmospheric pressure and density in only about a 16-kilometer altitude change. With this information in mind, let's track Booster 10 from 50 kilometers here, where it was T plus 603 and the grid fins became initially operational. And here's a comparison of a Falcon 9 RTLS at the same location. You'll note that the Starship is about 31 seconds ahead in time, but 890 kilometers slower at this point. So let's let Booster 10 continue to descend to 40 kilometers, and you can see the atmospheric layering that it is passing through at this point. Stopping at 40 kilometers and comparing to the Falcon 9 RTLS at the same point, what we notice is that Starship has gotten to the 31 seconds ahead, and it is now 216 kilometers per hour faster. This is a result of not having that entry burn. Let's continue to let Booster 10 descend through the atmosphere down to 30 kilometers and, of course, the atmospheric layers that it's passing through. Pausing here at 30 kilometers, comparing to Falcon 9 RTLS, we see the dramatic difference that the entry burn makes. At this point, the Falcon 9 is finishing up the entry burn, and the Starship is now 34 seconds ahead and 1,532 kilometers per hour faster than the Falcon 9. And this is important because all of this extra energy needs to be dissipated with aerodynamic drag further into the atmosphere. So here we're following Booster 10 further into the atmosphere down to the point of first initial instability, which was about 21 kilometers. Pausing at 21 kilometers gives us an insight into what is starting to happen. Now, this is the first point of instability. We can see that this is at 6 minutes and 29 seconds. The Starship is traveling at 1.2 kilometers per second at this point. And this is probably the last point of nominal trajectory. Now, we can also compare to the Falcon 9 at this exact same point, and we see that Starship has now increased its time to 39 seconds ahead and 1,433 kilometers per hour faster than the Falcon 9 at this point. So let's let Booster 10 continue down to 15 kilometers. At 15 kilometers altitude and 6 minutes and 34 seconds of the flight, the Starship was still traveling very fast at 1.09 kilometers per second, and maintaining proper attitude for deceleration began to become difficult. This is a comparison to the Falcon 9 RTLS at this same point in time. And one of the things that you will notice is that the Starship continues to get faster. It's about 42 seconds faster than the Falcon 9 RTLS and 1,023 kilometers per hour faster at this point. So this is Starship as it continues to descend now down to 10 kilometers. Pausing briefly here, we see that we're at T plus 6 minutes and 39 seconds. Starship is still traveling very quickly at 0.86 kilometers per second. Instability is dramatically increasing. Here's a comparison of the Falcon 9 RTLS at this exact same point. And what we see is with that increase in speed relative to the Falcon 9, Starship is 47 seconds ahead and 1,394 kilometers per hour faster. Still a lot of energy to try to dissipate. Now let's progress down to 8 kilometers. At this point, Booster 10's descent profile is dramatically different than what we see with the Falcon 9 RTLS. It's continued to accelerate more, 48 seconds ahead and 1,271 kilometers per hour faster than the Falcon 9 at this point. At 5 kilometers in altitude and T plus 6 minutes 45 seconds, Starship is still moving quickly, 0.58 kilometers per second. Instability is increased to the point where it is pretty much out of control. This is what the Falcon 9 RTLS looks like at the same point, and Starship is 54 seconds ahead and 944 kilometers per hour faster at this point. Continuing to descend down to 3 kilometers and T plus 6 minutes and 49 seconds, we see that Starship is still moving quite quickly, 0.45 kilometers per second. That means for about 2 seconds, we get a kilometer in altitude loss, and at 3 kilometers, that's pretty significant. Also, it looks like they are out of the parameters for a successful engine start, even if that were possible. The Falcon 9, by comparison, is already into the landing burn and significantly slower. Starship is 58 seconds ahead of the Falcon 9 time and 710 kilometers per hour faster at this same point. Continuing the descent, Booster 10 is now completely out of control at 2 kilometers in altitude. As comparison, Falcon 9 is well into the landing burn, only 743 kilometers per hour. Starship is 57 seconds and 597 kilometers per hour faster at this point in time. Now also at about 1.7 kilometers is where the engine start was initiated. That's at 6 minutes and 54 seconds. Starship was traveling at 0.37 kilometers per second, or for every 3 seconds it would be a kilometer, and that is very close to the water. Also, the engine start was significantly later in altitude than what we see with the Falcon 9, and of course with the 6 disabled engines it never really had a chance, and even with the 7 remaining engines, only 2 of them really lit. And given the speed that it was going as time and the altitude, there's really no chance for that to happen. Now, the Falcon 9 at 1.7 kilometers is only at 815 kilometers per hour at this point in time, a slight difference from what we saw at 2. However, the Starship is now continuing to accelerate at 58 seconds ahead and 597 kilometers per hour faster. So only in 0.3 kilometers, it's dramatically changed even compared to the Falcon 9 at this point. So let's take a look back at the comparison of the descent profiles between the two rockets and look at some of the lessons learned or observations that I've made that I'll be looking for in Flight 4 to see how successful the booster return may be and some of the changes that SpaceX has made. Also, this will give us a good insight into the likelihood of a Flight 5 attempted catch or not. Now, the Falcon 9 RTLS and the Starship booster have very different profiles, at least comparing what we had for Flight 3 and what we see with a typical RTLS. Now, of course, I know that these are different systems, they're different sizes. The areas of the booster is significantly different than the Falcon 9. The weights or the masses are very different as well. I understand that, but right now we don't have very many examples to go on, so that is why I'm drawing these conclusions, or at least these comparisons, to come up with some observations that we can look for. Now, in the region that I have highlighted, the Starship booster just has a lot more energy to dissipate than the Falcon 9. This is partly because of the entry burn that Falcon 9 does, but for the booster for the Starship, they've elected not to do that, and there's various reasons why. Maybe that'll be something that they reevaluate, or perhaps with proper control, they'll be able to get the aerodynamic drag that they need to be able to dissipate this energy. We also see that the proper and full booster control during this period, especially as the atmospheric density starts to rise rapidly at around the 20-kilometer point in time of altitude, and that will be needed for that dissipation of energy with the aerodynamic drag. Also, with the higher energy base that the Starship has to start with right now, this is why 13 engines lighting and being able to provide a significant amount of thrust initially to arrest that descent rate is critical. And if they aren't able to get all 13 engines, then I think that it's pretty clear that the landing is not going to be successful. Now, after they've arrested the rate and got the energy where they need it to be, they can start shutting down the engines, most likely doing the catch with 3 engines. But this profile we saw with Flight 3 really illustrates what they need to do with this descent profile to ensure that the catch has a chance for success. And we also will see, based on some of the timing differences for Flight 4, that the landing burn is going to happen about 3 seconds faster or earlier, which means that based on the speed of the booster, that's about another 1.5 kilometers or around 4 kilometers in altitude for that landing burn to start, versus what we saw in Flight 3 at around that 2.5 to 2 kilometer range. So this will be something that is important to watch for during Flight 4. Let's take a look at the timing differences between Flight 3 on the left and Flight 4 on the right as provided by SpaceX. One of the things that we notice for the boost back burn startup for the booster is that there's less time from hot staging, approximately 7 seconds for Flight 4 than it was for Flight 3. This may be related to what they've discovered with filter blockage, or maybe some other issues that had to do with why the initial 6 engines shut down prematurely on Flight 3 and was part of the reason why the landing burn later on in the profile was not successful. But this means that very quickly after that hot stage, we should see the boost back burn beginning, and that's even while the booster is changing its attitude to do a retrograde burn. We'll also see a significant change for Flight 4 profile versus Flight 3, and that is with the jettisoning of the hot staging ring. This is scheduled to happen shortly after the boost back burn is completed. That would be at about 105 kilometers in altitude, and the explanation from SpaceX is that this is to reduce the booster mass of the final phase of flight. Now, we know that the hot staging ring is about 9 to 12 tons in mass. It's at the top of the booster, and this was added on after the booster design was essentially locked in, at least for the phase 1 of the boosters. And this can cause some problems, one of which is not only just the mass, which would affect the amount of propellant for the landing burn and what is available for arresting that energy that we talked about that we saw in the descent, but it also may relate to a controllability issue which has to do with where the center of mass or the center of gravity is in relation to the center of pressure or the aerodynamic center of the booster on the descent. And I can get into that in a different video, but generally speaking, the changes of the distance between the center of mass and the center of aerodynamic pressure greatly affects the controllability of the rocket on the return, and perhaps that was one of the issues that they are trying to address as well. And as I alluded to in the earlier part of the discussion, SpaceX is also doing the landing burn 3 seconds earlier based on the speed that the booster will be traveling at approximately that time. That will add about 1 kilometer or so in altitude. That gives you more time for that engine ignition to occur, to stabilize into the thrust needed. and then also to arrest all of that energy that it should have at that point in time. Now, if they have controllability through the thicker parts of the atmosphere, more of that energy can be dissipated through aerodynamic drag. So hopefully that will be a bonus, and also with this higher altitude should give the booster more of a chance of having a successful landing attempt and simulated landing catch in the Gulf of Mexico. So now, with all of that being said, the reason why I took this exercise on was to try to give me some milestones to look at during the actual launch and return of the booster during the actual event. And hopefully with these indications, we'll be able to get a good gauge on the booster performance on the return for Flight 4. On the left-hand side of the screen, you can see the set of milestones based on altitudes, time, and key aspects of each of those particular milestones that we need to be looking for during Flight 4 and the booster return, and also a speed profile of what we should be seeing as far as how fast the booster is moving at these specific altitudes. And that'll give us a great indication during the live stream of how well Booster 11 actually is doing, or maybe not so well. But will also give us a really good indication of whether or not SpaceX is getting the data that they need, and hopefully a nice controlled, slow splashdown simulated catch in the Gulf. I'll also be watching to see if the actual chopsticks on the tower are being used to follow along and simulate that catch as well. One other aspect is if the visibility is good, we may actually be able to see the booster coming back and splashing down in the Gulf. If everything goes as planned, it should be about 30 kilometers or approximately 20 miles to the east of the launch site in the Gulf of Mexico, and that could be close enough for good visibility. Well, there you have it. Some analysis and observations that I made during Flight 3 and projecting into Flight 4, what we may see coming up here in the near future. Now, I hope that you found this discussion helpful and informative and maybe thought-provoking as well. And also, I wish SpaceX all the best for a successful booster return and getting a lot of data so we can find out if we can do a catch on the next flight or not. So thank you very much for listening and for watching. I do very much appreciate your support. Have a great day. Take care.